3 more presentations today after this short break. And our first presenters from KU Leuven University. This is a group of researchers led by Jan Vanthienen. And people in this community know Jan very well. He even has special name, decision table professor, because he was one of many of some people who initiated the entire movement. And Jan and his KU Leuven colleagues contributed a lot into design, theory, and practice of decision intelligence. And they continue to provide very interesting research year after year. It was extremely interesting presentation on previous DecisionCAMP. And today they have even more intriguing topic to present called extracting decision models from images. I'm just really looking forward to see what you guys did. And Jan and Caroline and Aurelie, go ahead. Start it.
Okay, thank you, Jacob. Thank you for the nice words. We try to do our best. This year, indeed, we have a special presentation, of course, about DMN and decision models. And most of the presentation will be handled by our 2 excellent students who finished their studies and are now starting in a job. And the other co-author is Alexandre Goossens, who just finished his PhD in decision modeling, of course, and will now move to Paris and work for a data science company. Just as an introduction, you can read the full description of our bios there. Caroline will be presenting and Aurelie will be presenting. What is the topic for today? You see the overview here. The topic really is, okay, you build a decision model. Probably first you start from scratch, you start on paper, you start in a bar and then you draw something on a paper, or you have a printout, or you have a Word document. You have something that resembles a decision model. You have a DRD, decision requirements diagram, or you have a decision table or more decision tables. And of course, once you have done your first attempt, you want to get this into a tool, but you don't want to go over all the manual effort again to type in names of decisions and requirements and data items and all these things. So the research question we had was, would it be possible to read a decision model, the DRD and or the tables, just from a handwritten document or from a printed document? And as far as we know, there has been no research in this area. So we tried to address this gap by using deep learning to extract DMN models directly from images. The images are drawn by people, hand-drawn, or are printed, digitally drawn on paper. And we try to use deep learning to come up with a decision model in the form of an XML file. So it's a real model, digital, starting from a digital or from a handwritten model, and try to build up the DRD and the decision table. Why would we do this? Why would this be useful? Assuming it works, and they will tell you everything about does it work, yes or no. But assuming this works, why would we do this? Well, they are often there. They are printed, they are in documents, the tables are there, the DRDs are there. And manually converting these images into files and typing in all the information and then in a tool and then generating all this information into DMN files, XMN files is a little cumbersome. So it would be nice if this could be done automatically. That's what we try to do. Try to extract the DRD, try to extract decision tables from images, combine the two, link the table to the DRD, integrating these into a coherent, legible DMN file. I'm not saying we should use this to output a DMN model from one tool and input into another tool, because that is a standard procedure that will work. But if you have a printout, that's the way to do it. So the focus is the extraction. The focus of the extraction is on digitally drawn, hand-drawn images, assuming we have them, and we have lots of them, of course. Of course, we don't do the entire DMN. We use DRDs, we use the decisions, the boxes, the requirements, but not all the final details of the latest version of the standard. And we also will use the tables and try to recognize the tables using these deep learning. There are some assumptions, because this is a proof of concept, and then I will hand over the floor to, I think, Caroline. A few assumptions are that we start small, meaning we don't look at complicated images, multiple images on one page. We start with a single image with the most common visual elements of decision models, the decisions, the dependencies, the data sources, information items, the rules, the table, not collections and so on. Only the elements that you can see in the picture, not something that is behind the context menu, the details of a hit policy that are hidden in a context menu. Of course, it's hard to recognize. And therefore, these excellent students have made a manual annotation of a large number of models and try to learn from this how to recognize decision models. And they will tell you how many models they used and trained and draw and so on. We only use images, no glossaries, no domain knowledge, no ChatGPT and so on, just the basic image recognition. Okay, I leave it to you or to them to tell you how this went, what the purpose is, and how this succeeded. Who will start? Aurelie, I think, or Caroline?
Yes, I will start. Thank you.
Okay, go on.
Okay, so now I will start telling you how we approach this, because yeah, it's really a great thing to do, a great thing to think about, and we really want to get to the purpose of extracting useful information from our images we created, so both digitally drawn and hand drawn, as Jan already said. So we had to think about like how will we approach this, and this is shown on the slide now. So first, we of course created a data set. So this means that we went to a lot of research papers and also the object management group. We used all these DMN models, and we also hand drawn all these models manually. Whenever this was done, we were able to actually begin with the work. So then we have chosen to classify these images into what is shown here, so digitally drawn and hand-drawn images, because we used different models for both. And also we decided to split up into a DRD image and a decision table image. So no images were used where DRDs and decision tables were combined. So we really chose to, separate everything. Then, of course, the images need to be pre-processed in order to, of course, enhance the quality, to get the most out of our models and our end results. Then we started with the actual extraction. So first, the decision requirements extraction. So everything to be extracted from the DRDs, and then the decision logic extracted, everything to be extracted from our decision tables. Whenever this was constructed and done, tested, we need, of course, to match the DRDs with the corresponding decision tables. So this is what was taught about and done in step 6. And then we are ready to show the DMN model found in the images. And then the last step, of course, evaluate everything. And Caroline will later on show you our outputs and our actual results, some numbers, etc. Yes. So I want to say a little bit more about the actual extraction. So the step of the decision requirement extraction and the step of the decision logic extraction. So this one is for the decision requirements, so the DRDs. We split it up in object element detection. So these are the decisions, the inputs, the knowledge sources, and so on in the first image in the left corner. And then the detection of the object requirements, so the arrows in the other images, the other image below. For this, we have chosen to work with Detectron 2. This is a framework with a lot of pre-trained models, especially to be used for detection of objects in images. So let's say a share or whatever you want to detect in an image, and we used it to detect arrows or squares, circles, etc. To be more specific, these are neural networks, and we used faster RCNN and key points RCNN to detect the decisions, inputs, and then the arrows respectively. These models are then able to give us some coordinates, so where are the actual objects detected located, and a label to know which object it is about. So 1, for example, for the decision, 2 for the input data, and so on. In a third step, we then need to detect the text within the objects. So that's what we did. And we used Tesseract OCR. That's a Google application where you can detect your text. This was quite challenging, as Caroline will say later on. But whenever the object and the text is detected, everything here is now ready to link the text to the objects and the arrows to the decisions or the input data and so on, as can be seen in step 4. And for the decision logic extraction, we have the same story actually. So again, we want to detect our objects, which are now a table header or an input, a row, and so on. And for this, we experimented with faster RCNN again, but also mask RCNN, 2 neural networks, again in the Detectron 2 framework, because we found that detecting objects in a decision table is more challenging than a more simple DRD. So that's why we experimented with both. And again, our models give the coordinates and the labels. Then the text needs to be detected and everything needs to be linked together again, kind of similar to the previous slide. Then in the following step, as already said, now that we have everything, we need to match our decision tables to our DRDs. And for this, we thought about a little algorithm where the Liebenstein distance is calculated between every decision and the a corresponding decision table header, in which every Liebenstein distance is calculated between all of them, and the minimum is is the one or the pair that will be linked. So what does Leuvenstein distance means that is basically just the number of characters that are not similar. So for example, lone grade and lone grade, as the picture shows, that's of course Leuvenstein distance of 0, but matching lone grade with grade, that is Leuvenstein distance of 5, because 5 characters are not the same. And then when we also have information about the linking, everything can be generated in an XML file typically used to generate our DMN model. And
Okay.
finally, I would also, oh yeah, okay, you can do it too, it's fine.
Sorry, misunderstanding then. But do it. Go ahead.
Okay, so finally, then Caroline will go further into the test results and so on. I want to say a little bit more about our actual data set that we made. So we made 2, one for the digitally drawn images and one for the hand-drawn images. And as you can see in the third row, we collected 62 DRDs for the digitally drawn and 130 for the hand drawn, so quite a lot. And on the row below, you can see how many elements this is, so how many the sum of how many decisions input data in total. So this was quite extensive already to train our models and get some working results. And then you can also see a bit lower how many decision tables we had, 74 and 126 for hand-drawn. Why was hand-drawn bigger? That's because it's more challenging in the first place, but also we wanted to really incorporate different handwritings of people so that our models not only learn from one person. So we asked colleagues, friends, and so on to also draw a DRD. So we had 2 or 3 times the same DRD, for example, but with different handwritings.
Okay, so now that the approach is explained, I'm gonna dive into what all this approach leads to and how the actual output of the algorithm looks like. So all the models were integrated into a tool to show how it works. So on the slides, you can see an overview of how the tool looks like. So it's very simple. It's not meant for the public or anything, but it's really to show how everything works together and how the models were integrated together and so on. So maybe, yeah, I think it speaks for itself. So the user can upload an image of a DRD and then an image of a decision table, which can be either handwritten or a digitally drawn /PDF. And then just by clicking on the converting button, the user will eventually get the model implemented in DMN. So those are some examples of how it works at the moment. So for example, this is an example where it works pretty good. So the input on the left gives the output on the right. So you can see that, for example, there is some missing arrows, but with a few clicks, the user can really get the whole DMN faster than if he or she had to start and redraw every element of the DRD. So this is another example for a handwritten DRD where it also works quite good. Sometimes you can see, for example, yeah, here it's really, it works well because we took a good example, but you have to imagine that in some other examples, not all the text is being detected, or some text is being associated to the wrong element or so. But this is, we took some good examples to show that it does work. So for the tables, same. So this is the input and the output. And you see here, for example, with the text detection, that the hit from hit policy is also getting put in the input element of the table. So that's a bit annoying. And for example, here, there is no, I mean, the text isn't being detected. So that's a little bit more of a challenge with tables to detect, especially because of the structure of the table, and also because the text detection also for DRD or for the tables, the text detection is kind of challenging. And within a table, if the text is not being well detected, it makes a lot more, it's a lot more annoying within a table than within a DRD, where you can just see the shapes and change faster the text if there is some spelling mistakes and so. So voila, for a handwritten table, this is even more problematic. And in a lot of example, the table wasn't even shown because it was missing some inputs or outputs. And so if the if DMN doesn't see any input within the table, it can't show the table, and so the prediction of the output weren't like shown either. So that was a lot more difficult for a handwritten decision table. But yeah, so those were examples, and I'm going to show you some test results. It's maybe says more, and it's a little bit more objective. So for the decision requirement level, so to be clear, the DRDs, the object detection model is the one detecting the shapes within the DRD. So we have a pretty good average precision of 0.9 for the digitally drawn DRDs, and a little bit less good, but still good precision of 0.7 for the hand drawn. And that's for the decisions. So the other elements have some precisions that are a little bit lower, due to the fact that in our data set we have a lot more decisions. So the model is better at predicting decisions than other elements, but this could be easily resolved by adding more of those elements in our data sets. For the key point detection model, so that's the arrows within a DRD. We also have some good good numbers. So again, the best average precisions are for the information requirements, due to the fact that there is a lot more information requirements with in our data set. And again, the results for digitally drawn images are a little bit better than hand drawn, but this is to be expected, I guess. And for the text detection, we also have some better results in the digitally drawn compared to the hand-drawn text detection, which was kind of a challenge due to the number of different handwriting styles. So those are kind of the results and the limitations. But for the decision requirements level, we think that the limitations can be addressed by augmenting the data set and maybe also test other text recognition techniques. So we used Tesseract Dossier, like Aurelie talked about, and like it was also shown in the general approach, but some other OCR models could also be integrated within the whole algorithm to maybe improve those metrics. Now diving to the results for the decision logic level. Like I said, the results for the decision logic level are a little bit less good. So for digitally drawn, we have for the decision, I'm not gonna go over all the numbers, but the best results are we get the best results with the mask or CNN for the digitally drawn. So between the two neural networks that we tested, the mask or CNN is the best. But for the hand drawn, the faster CNN gives slightly better results, although the results are here below 0.5, so not very good. And again, for the text, we have some similar metrics as for this decision requirement level. And again, some other techniques could be used. And to address the limitations in the table detection and table elements of the table detection, we could also increase the data set by adding additional styles and so, but maybe some alternative techniques for the table recognition could be tested. We thought about some more post-processing, like if there is no input, add an input, like a random input and so on. So we've had some ideas to improve those results, but they aren't implemented yet. And last test results that I will talk about are the results for the whole model generation. So like I said, the models for the decision DRD and table are all integrated into the tool. And these are the results for the whole tool. So one table plus one DRD, and we looked at the outputs, and that's how we calculated the metrics here. So again, the DRD's elements have pretty promising metrics. Requirements also as well, and the tables elements are like the pain point of the tool. And as expected, for the hand-drawn images, we get lower results, and even for the DRD's elements for the hand-drawn, it was a little bit more difficult due to, again, the different handwriting styles and so on. About the limitations for the whole tool, we wanted to underline the fact that there are some restrictions regarding the evaluation in the sense that we had to count every element by ourselves, and it's not I mean, there could be human errors, or also there is not as many, like we used some good examples, I mean restrictions in general, but some ways to improve are to enhancing the DRL and DLL models, like I just talked about, and also within the tool integrating additional error and handling and exceptions mechanism so that we get less errors or just blank outputs, addressing like the times of transforming the DRD and the table, and also allowing to incorporate more than one decision table for one DRD, because we know that in real life, most often one DRD has one or more decision table, and also eventually integrating the latest advancements of DMN within the tool. But those are some future works. So yeah, I'm gonna skip this because I think said all the points here. But to conclude, we have good results for the screenshot, especially for the DRD especially, but we have some lower results for the tables, but a lot of possibilities to improve are available, and especially with the advancements in the field of image recognition, text recognition, and so on. So we wanted to, we have as a conclusion of all this work that the use of deep learning models to extract DMN from images is feasible, and it could really be helpful in the industry for business users that don't want to spend time modeling remodeling something they have sketches and so. But of course, this is an example of a tool where everything was integrated, but there is some limitations that still could be addressed in some next work, hopefully, or voilà. So that's it for us. Thank you for your attention. And if there is any questions, feel free to ask. I don't know if I can see the comments. But if anything,
chat.
Sorry?
Click chat and you will see comments and questions. And Ellen has a question to you. Thank you very much, first of all. It's really very interesting what you did. And now we have questions. Ellen, can you just go ahead?
Yes, that's very interesting, very promising. Thank you. I'd be interested to know how feasible you think it would be to introduce some sort of validation of the models you're generating. I noticed that in your examples, you're generating DRDs that weren't actually valid. Is it possible to disambiguate the interpretation of the images by validating what you're creating, or would that actually get in the way of perhaps authentically reproducing invalid diagrams? I don't know what your intentions are.
I think it's pretty, I wouldn't say easy because it requires a lot of coding, but we could use some post-processing and add some exception mechanism to maybe even send, like if we wanted to really make this application for business users, we could easily, or at least it's feasible to send like, oh, your DRD is not valid because please try to change this or so with some coding and some time to spend to coding, I think it's quite easy.
Yeah, so I was more interested not in noticing validity problems with the provided DRDs, but in removing errors in the transcription process. So if the drawn DRD is actually valid, then you should be able to tell that your version of it isn't valid. There's obviously some sort of problem. Might be a way of distinguishing between possible interpretations of the drawing.
If I can jump in here, there's actually some interesting work by some colleagues of you in Leuven, a group of Tias Gans, who build a Sudoku assistant where they interpret a handwritten Sudoku grid and use the constraints to actually understand whether this is actually a 6 or a 9 or something like that. So you use knowledge about the structure of the problem that you're acquiring to improve the recognition of the image. And so I think with these diagrams, it should be possible in some form to do something similar.
Mm-hmm.
Yeah. Okay. You have a few more questions, and I just wonder if you just, this is quite interesting confirmation of what Denis said before about augmented intelligence, because you want to provide new, more human interface to decision modeling, right? So this is intention certainly very, very good. And because like Helmut gave you reference to your colleagues, and also there are so many activities in this direction. For example, so I wonder if you look what Copilot or other LLMs, ChatGPT can do in this direction without creating anything. It's quite powerful. Let me just, what I mean, I will show you just for a second. I will share my screen and I will tell you what I mean. Okay, let me share my screen. So you can see the screen. This September, we published this DM Community Challenge, Rental Bots. And this is the text of this challenge. And this was plain English text with some unrelated information, like send your solutions to DM community. But data for this challenge was presented in image. It was not, this is a pure image, a PNG image placed inside HTML presentation. And I just decided to talk to Copilot, and I gave Copilot this, just copied and paste everything. And immediately Copilot produced, look on this image and look what is produced. It extracted smart information about actual semantics extracted from this text in form of constraints. And then it took this table and provided data summary, and it was 100% correct. Look, it says here, it takes bots and it takes different types of bots, everything without a single error, and everything was correct. Everything was great, and even their solution was good, but it was not really optimal. They made one mistake and generated decision model. In this case, they just generated Python, but it does not matter. They did convert it plain English and plain images into correct working and executable decision model. This was quite amazing without any extra tools. So just, I think being skeptical about hallucinations, we still should look at capabilities of LLMs. And I'm not sure, I would recommend you to look at this as well, using not necessarily this, but Okay, can you share your screen again?
Yeah. No, I have to. No.
Okay, more questions, please. That's... Yeah, what is great about universities, they always bring some unexpected perspective to common points of view, and this is the confirmation of this. You did very interesting research, and look how many ideas it brings. I just put in the chat a link to quite old research did that MIT group of scientists did, I think it's more than 15 years ago. And what they try to do, if you click on the link, they try to draw picture, and automatically, for example, they created when you link, you will see what does it mean. And this was their idea of future user interface. Nobody talked about LLMs at that time, but they already predicted something. And I was lucky when I cooperated with University College of Cork. I was part of this team when we tried to create a constraint-based model based on this input. So it's a lot of activity, and it deserves much more. We can see, and we really appreciate that you openly show us all deficiency, and it's not exactly, there are some mess with mixing these words about heat policy and putting it in wrong place, but this is our reality, and I'm sure that if we keep moving in the right direction, one day we will have a nice, more human input.
Yeah, I'm sure of that, Jacob. This is a first attempt. It's 4 months old, so we are now 4 months further. So probably if they would have to do it again, it would be even faster and better. But it shows a direction. I think there's promise in this area.
Yeah, and it would be very interesting if your colleagues can work on this MIT, and in general, it's interesting to revive this research, because it was quite shocking results, and it's so attractive to draw, not just to photograph with your camera something already created, but to just draw, and in real time you can see how this model is being updated in real time without creating any intermediate files. This is the direction what would be extremely, it's just opposite to everything what we did so far.
Yeah, and as Alan is saying, it would be a good opportunity for immediate feedback while you are drawing or while you are building your model. Great. Yeah.
Exactly. Yeah, that's quite interesting. And good. So any more questions? It's quite interesting topic. No more questions. Okay, good. What is interesting that next we're just talking about human interface, and our next presenter will talk about human perspective of everything what's happening right now in our ecosystem. And exactly in the top of next hour, at 1 p.m. o'clock, Alan Fish will present and share his experience in this area. So we will take a break until 13:00. Thank you. Good presentation.
Thank you.
Right.
Stop.
Yeah, I will stopping this. Thank you.